Okay. So if you follow the instructions for remote login, you should be able to connect to the NetFort server. And in my case, I have a shortcut. Then I enter my username, my password. So Linux will look like this. And if you double click my computer, it pops out this one just like my computer for our Windows system. But honestly I don't like this because every time I click anything, a new window will come up. So it's really a mess. Typically what I do is I'll go to application. There is one application called file browser. You can just drag it to your desktop. So now I have this file browser here. This is more like what we have been using in Windows. And you have this address bar. You can enter the address, type the address, or you can double click any folder. And you can also use internet, so just click this symbol. Then let's go to Blackboard because we need some files from Blackboard to set up our Cadence simulation environment. Log into Blackboard. Yeah, it always happens when I want to do EDA tutorial. The network becomes very slow. Okay, and go to our course website. And under the Cadence folder, there is one file called Cadence files. So I'll simply save this file. And after download is complete, I'll have this guy on my desktop. So I simply need to double click it. It's a zip file, and I can click extract. So everything is the same as a Windows system. Then I'll have this folder extracted. It's called Cadence files. Okay, if I open it, I can see one file and one folder. But if I do view, show hidden files, then we can see more files. And those files are related to the environment setup. So what I'm going to do is I'll open the file browser. And I'll drag this .bashrc. This one is for the entire environment of your Linux account. I'll drag it into my home directory. And the reason I call it home directory is because once I open up the file browser, I'll go to home / and this is my account name, right? So this is called my home directory. And I'll do the same thing, view, show hidden files. And now as we can see, I have this file .bashrc over there. And the next thing is I'll create a folder for the course project. So I'll call it ECEX321 2012. Go to that folder, and I'll drag the rest of the files to this folder. Okay. So among these files, .cds environment basically determines your Cadence environment setup. .cds init is the initialization file. It initializes the Cadence environment. And this one, .cds plot .nint, it determines how you are gonna plot the waveform after simulation. And the CDS.lib, this one, determines your CDS library, what kind of library, what kind of process you have in your design environment. And under model folders, those are the model files that describes the performance of the transistors. Okay, so very simple, that's all what we have to do before we can run Cadence. And now I right click, oh no, I don't have terminal here. And now on the desktop, I right click and I choose open terminal. And then I have the command environment. From Blackboard, you can download a file that lists all the useful Linux command. So what I'll do is ls, which lists all the folders and files under my home directory. And now I cd into the folder I just set up, which is ECEX321_20. Actually, once I type those things, I can use a tab. It will automatically fill in the name of the folder, right? So now I'm inside this folder, I do ls, and those are the files I just moved into the folders. If I do ls a, then it will display the files with the hidden files. Okay. All right. So basically that's it. And what I can do to bring up the Cadence environment is I can type ICFB. And after ICFB, I'll have two windows. The first window is the kind of center of the Cadence simulation environment. It's called CIW. And the other window is the library manager. So in the library manager, we can see we already have multiple libraries. Most of the libraries are related to the process we are going to use, which is AMI06. This stands for AMI semiconductor 0.5 micrometer process. And 0.5.6, as I said, analog designers, they are not accurate. So 0.5, 0.6, they mean the same thing, okay? All right, and now I have to establish my own design library. I can't change anything here. And actually, you don't have the permission to change those NCSU libraries. So we have to do File, New Library. And I'll name this as EDA1. Okay. And I click OK. After that, this is important. For this window, I have to choose attach to an existing text file because we have our design process, which is AMI 0.5 micrometer. I click OK. And here on the drop-down list, I'll choose NCSU TechLib AMI06. Okay. After that, not much change. So I just added this library called CDA1. And now I do File, New, Cell View. And for the cell view, this means the name of the schematic I'm going to establish. Okay, and later on you can change this to for layout and other purpose. So for the first cell view, how about let's do homework 2 together. So I'll name it as homework number 2, schematic. And after that, I got this window automatically popped out, schematic window. So on the schematic window, I have to put the transistors and the signal source for simulation, right? And from Blackboard, you can download another file, which is called Cadence byte keys. Those Cadence byte key means those are the shortcuts you can do without using the menu. So for example, the first important byte key is key I. So I means insert instant, instance or component. So on the schematic window, I hit the button I on my keyboard. And right here, I have to choose the correct library. So on the other window, I'll choose library NCSU analog parts. And now I go down to N-type transistor. I'll choose NMOS4. This means a 4-terminal NMOS device. Okay, and if I want to zoom in for full screen display, I can use the byte key F, like this. And now I select this transistor and I use byte key Q to change the property of the transistor. So anybody has homework number 2 that can share with me? Thank you. Okay, so for homework number 2, problem 3, we have to simulate a transistor. Let me do it a little bit more professional. Homework number 2 is right here. We have to simulate for the IV curve of NMOS transistor. All right, and the size is width 19.95 micrometer and length is 1.35 micrometer. So I go down, I change the width to 19.95 micrometer, and I change the length to 1.35, and I have to type U, which stands for micron. I don't have to type M, so like this. Okay, it's good enough, and I use tab, it will automatically fill in the M. Okay, and this is the size of the transistor I'm going to simulate. And now I have to add other component. So I use hotkey I, and I can go to analog library, choose source, global source, and there I have GND, which stands for ground. Okay, and in the future, once you get familiar with this, you don't have to use this window. You can directly type the name of the cell in that library. For example, I want VDC, which stands for DC voltage. I'll add this DC voltage here, and I use hotkey W to add wire. And I use hotkey C to copy. And the nice thing for Cadence is you don't have to use control. You simply hit the key C, and that's it. And for the body terminal, where shall we connect it? It's gonna be connected to ground, right? Okay, and I have to get a drain source voltage for the transistor. So I'll copy this over there. And for the gate voltage, you can set the DC voltage here, for example, 0.8 volt, or you can define a variable VGS, stands for gate source voltage. And for drain source voltage, I'll define another variable. I'll call it VDS. Okay. After that, I have to always check and save. If I don't do this, the simulation doesn't run. Okay, so I have to click this button over there, and I go to Tools, Analog Environment. This will bring up the ADE, which stands for Analog Design Environment. And right here, I have to first set up the simulator. We are going to use Spectre as the simulator. Click OK. And later on, I'll tell you how to use this to set up fancy things such as remote simulation and OceanScript. Okay. And now we have to set up the model library, because for the transistor, we have to assign a model for it, right? Different foundry will have transistor with different performance. So with this window, I'll choose Browse. And this opens up my project folder. and I'll double click this model folder, and right there I'll choose ntt.typ. This represents the model for n-type transistor in typical case. Okay, I will continue to add ptt.typ. And for the rest of the model files, you can use it in the future for corner simulation, which represents different process corner. You may have slow process, you may have fast process due to fabrication error, right? So, but for now we use the typical performance. So I have PTT for PMOS, and I click the button Add to add it over there. Now I have two model files, one for NMOS, one for PMOS. Click OK, and I go to Analysis, choose the right analysis. And basically for the first homework, it's gonna be very simple DC simulation. For DC simulation, I'll choose Save DC Operating Point and click OK. And now right here on the analysis window, we have the DC simulation. And remember we defined two variables, so I can go to Variable, copy from Cell View, and the two variables will be automatically propagated here. And I double click this variable, I have to assign a value. For example, for VGS, I determine it's gonna be 1 volt and click change. And for VDS, I change it to 3.3 volt, click change, and now I click OK. After all of this, the first thing I want to do is to save my session, save my state, save all the setup. If I save this, next time I only have to load this. I don't have to redo all the things for simulation. So for save, I have two options. I can either save it under the current directory, or I can save it as a cell view. And normally I'll choose cell view. Click OK. And I think now we are ready for simulation. So I'll click this traffic light button, which means netlist, and run. This will create the netlist for the circuit and run the simulation. And now simulation is finished. DC analysis is finished. I can go to results, annotate DC node voltage. So you'll see the node voltage already annotated. The gate source 1 volt right here, right? And for the source it's 0 volt, the drain is 3.3 volt, and this is the first step. And now I have to simulate the IV curve. So in order to do this, I double click the DC simulation and I choose to sweep variable. I'll sweep the design variable, and I want to plot the current as a function of VDS. So I will sweep VDS, start from 0 volt, stop at 5 volt, click OK, and I do simulation again. So see, now the DC simulation sweep all the parameters, sweep all the values for VDS. After that, I go to result, direct plot, main form. And from the main form, there are options like in the future, if you do more kind of analysis, transient AC, you'll have more options, but right here we only have DC. And for DC simulation, I can plot either current or voltage or power, things like this. And I'll choose to plot current. And I'll plot the terminal current, and on the bottom it tells me select instance terminal on schematic. So I go back to schematic. I'll select this terminal of the voltage source. So this terminal basically it represents the current for the drain, right? So I'll just click this terminal, and now we have one curve. And does this curve make sense? This side it's linear region, right? And this side, suppose it should be very flat to the first order approximation. but we have channel length modulation, so it's skewed slightly. And the next thing is I have to plot the current versus VDS for different VGS. So I go to Tools, Parametric Analysis. And right here, we can add another variable, VGS. And the range for VGS, I'll sweep it from 0.8 volt to 1.4 volt. And I'll do linear step sweep. So the step size, I can choose it to be 0.2, which means we simulate for 0.8, 1, 1.2, and 1.4. Now I go to Analysis, Start. So this is like we add one more dimension to the sweep, right? So now the simulation is finished. I close this, and I go to Result. Okay, on the result window, I can actually I'll close this first. Okay, go to Result, Direct Plot, Main Form, Current, and I plot the current again. And now this is drain current versus VDS for different VGS, right? And on the top, it shows what is the value of VGS. And to this step, I want to save the result and submit the homework. So I can either do a screen capture, or I can go to Window, Hard Copy. And on the hard copy, I'll choose Send Plot only to File. And I have to specify the location where I want to save it. I use // which means save under the current project directory. And I'll name it as IV curve, and I'll save it. Okay, it's saved, but it's saved on the Linux machine. Then how can I plot it in Windows and submit the homework? One thing I normally do is I will install the small SSH software. Then I double click it, and I can choose to connect to a Langford. Password, and then this is still the command environment, similar to the Linux command, right? And I click this button over here. It enables the file transfer interface. So now on the right hand side, this is my home directory for the in the Linux account, and I go to the folder we just set up, ECEX321_2012, and I drag this IV curve to my Windows desktop, and I can use other software such as Acrobat Distiller to convert it into PDF format. If you don't have those software, you can simply do the screen capture. Okay. So once I have this PDF file, I open it, and the first page shows the user. And this is important when you submit homework. I hope you can somehow show that you did the simulation on your own account. You didn't just get the simulation result from your friend. Okay. And all right, and this is the simulation result. Okay. So now go back. I still have something to show, but if you are rushing for the next class, you can leave, because eventually I'll upload the video. Just leave quietly. I will continue to finish the homework. And the next requirement, I think, is to print the DC operating point for the transistor. So I have to find out the DC operating point with 0.9 volt VGS and 2.5 volt VDS. Okay, so I'll set up the value, and I don't have to do sweep. Okay, and simply run the simulation. And when the simulation is finished, go back to the schematic. So the result will be automatically updated for 0.9 volt VGS and 2.5 volt VDS. And now the tricky part is how can I find out the transconductance, GM, and other things like GDS. So I can go to result, print DC operating point. Okay. After that, see on the bottom of the schematic, it tells us select instance for the operating point output. So I'll simply click the transistor here. Now in the pop-up window, we can read out CGS, CGD, or the parametric capacitance, and we can read out GM, the transconductance. We can find out GMBS, which is the GMB in our class, right? And let's see if we have any other interesting thing. Okay, we have IDS, the drain current. Continue to go down. Okay. We have the voltage, the DC bias voltage, and you can find out VD set. VD set is a condition for active operation, right? This one is tricky. On the homework, I'll ask you to calculate the output resistance of the transistor, and you have to do it based on 1 over GDS, right? Calculate the output resistance, and you'll find out probably the value will be different from this. So, I'm already telling you the answer, okay? But the interesting thing is try to figure out what does this represent, RON. It's still something related to the resistance of the transistor, but it's not. It may not be the output resistance, small signal output resistance. Okay. All right. And the last requirement for this homework is to change the source voltage. Change the source voltage to 0.2 volt. So we can move this a little bit. And if we move it, we use hotkey M or S. And now I create a 0.2 volt voltage for the source, but my body, 0.2 volt. But be careful, my body is still grounded, right? Okay, after this, I can do simulation again. And after the simulation, you can read out VTH. So you have to analyze the change on the VTH, and this is obvious because once we give the source a different voltage, the VSB will change, right? Then secondary effect, the body effect, then VTH will change. So we have to analyze this change. We can go to result, direct print this operating point, and click this transistor, and you can read out the VTH and compare the change of the threshold voltage. All right. Let me see if there's anything else I want to mention. Oh, okay. One thing for very handy is when you do direct plot main form, you can plot the current, right? But before you do that, you can also check this, add to output. Okay. If you check this and you plot the current, you still have the current, but what's going to happen in the future is look at the ADE. The output is already added here. So it means next time when you run the simulation, I have already closed the waveform window. Next time when you run the simulation, suppose it will automatically plot the current versus VDS. Okay, but okay, the software is not very nice to me today, so okay. What happens is I have to check this. So after simulation, see now plot becomes yes, right? And after I run simulation, it will automatically plot the current voltage relationship. All right. Okay. I think that's all for this EDA tutorial. And if you have any question, feel free to come to my office, bring your laptop, and show me the problem. I can help you work on it. All right. Okay. Thank you. See you on Thursday.